Okay, thanks to the organisers. So today I'm going to talk about dark matter and gravitational waves from cosmic strings, but given the format of this talk, I thought it might be best to try to cover a few different topics. I won't have time to go through each one in detail, but I hope this will give some idea of the sort of problems that I think are interesting in this field and some of the challenges that we face. Of course, my choice of topics is very biased by the things I've worked on. This is not to say that other things are not interesting or important. So the first three of these are going to involve axion strings, and then if I have time, I'll talk a bit about metastable strings. So first I should define what I mean by an axion. So for my purposes, an axion is any pseudo-number Goldstone boson, let me call it A, and it's got an approximate shift symmetry A goes to A plus a constant. In this talk, I'm going to focus mostly on the dynamics of simple field-theoretic axions as opposed to closed-string axions coming from more complicated string theory compactifications. There's been some interesting recent work on the interplay or the similarities and differences between these types of theories. So for these field theory axions, I can think of a very simple Lagrangian, just a complex scalar field phi with the usual symmetry breaking potential. After spontaneous symmetry breaking, I expand phi in totally the standard way. R is the radial mode, A is the degree of freedom around the bottom of the potential. And let me define the axion decay constant Fa such that the axion is periodic with period 2 pi Fa. And for this talk, I'm going to assume that the mass of the radial mode is roughly of order the axion decay constant. It doesn't need to be at all precise, just not different by many orders of magnitude. Sometimes it's also useful to use the angular variable theta, which is just A over Fa. And on very general grounds, we expect that all global symmetries are explicitly broken at some level, for example, by quantum gravity effects. So in all cases, the axion will have some non-zero mass, which I'll call Ma. And for the people who work in this field, I'm going to standardize or simplify to the case of n is equal to 1 domain walls. It'll be easy to, in some cases, to extend what I'm going to say to other values of n. The stuff in the QCD axion, there are additional challenges going to larger values of n. Okay, so among these various different Alps, there's of course one particularly well-motivated one, which is the QCD axion. So in this case, the axion has a coupling to QCD via a term of this form, where G is the QCD field strength, G tilde is its dual. And provided this is the dominant contribution to the axion potential, or this leads to the dominant contribution to the axion potential looks something like this. So it has a height of order lambda QCD to the fourth. And the theorem of Vaffra and Witten tells us that the minimum of the axion potential is exactly at the position where the axion VEV solves the strong CP problem of the standard model. So if you like, the total theta parameter at low energies is equal to 0. A nice thing about the QCD axion is because all of its potential comes from QCD, we can write its mass solely in terms of the axion decay constant, and then a calculable coefficient, which we can get from, for example, chiral perturbation theory or the lattice. So there are, of course, many searches for axions, axion-like particles, experimental and observational. Typically, the coupling that is searched for in many cases is the coupling of an axion to photons with coupling constant Ga gamma gamma. And this is a plot from Kieran O'Hare of the current constraints in solid lines as a function of the axion mass. For the QCD axion, there's a particular prediction with a bit of model dependence, but not too much, that it should lie somewhere on this yellow band. There are also many proposed future experiments or observations, and if we get lucky and these experiments are successful, potentially the entire range of QCD axion masses down to like 10 to the minus 10 electron volts could be probed. So on one hand, this seems promising, but on the other hand, many of these experiments rely on the axion being the dominant component of dark matter, which maybe is not necessarily the case. And for a more general axion-like particle, there's no particular reason that it has to have a coupling to photons. Up here, it could be a much smaller coupling to photons. It could also have a much smaller mass, in which case many of these types of constraints just cannot lead to any interesting searches. So I think it's worth thinking about complementary approaches. And one that I'll talk about today is gravitational waves. So this is somewhat of an old plot and maybe in some ways more of a cartoon. But just to give an indication, if you look at the possible future sensitivity of searches for stochastic gravitational wave background, omega gravitational waves is the energy density in gravitational waves today, F is the gravitational wave frequency today, then potentially observations could probe down to pretty small values of omega gravitational waves. To do so, experimentalists are going to have to make use of course, many spectacular and extremely complicated technologies, ranging from pulsar timing arrays, interferometers, potentially in space, to ground-based interferometers, or potentially even atom interferometers. And there's both many experimental challenges to overcome and many observational challenges to, for example, remove foregrounds from black hole binaries. Nevertheless, potentially, this could give a route to sensitivity to new physics. And another nice thing about this type of probe of beyond standard model physics is we're potentially probing the properties of the universe at very early times. So for many sources of gravitational waves, the frequency of the gravitational waves today is correlated with the temperature of the universe when they're emitted. And potentially, if you look at something like ion, the Einstein telescope, or something like that, you could be probing the dynamics of the universe when it had temperatures of 10 to the 6 to 10 to the 8, maybe even 10 to the 10 GeV, which of course is far beyond any energy scales that we could probe directly in colliders. Of course, the downside of this is that there's no guarantee that whatever physics is active at those kind of energy scales will lead to a stochastic gravitational wave background. So it's not that it's a replacement for collider searches, but it is a useful complementary approach. Okay, now the cosmological history of axions broadly divides into two classes. So in the so-called pre-inflationary scenario, the Pecha symmetry was broken during inflation, such that if we look at the axion field configuration, here represented by the different colors on some slice of space, different colors representing different values of theta, probably this was initially random between 0 and 2 pi. But then subsequently inflation happened in such a way that over all that is now the observable universe, the axion field was initially spatially homogeneous to a very high degree of precision. And in this case, we don't know what the initial axion angle was. Maybe inflation happened and we happen to live in this patch of the universe here. Maybe inflation happened and we happen to live over here. In this scenario, the subsequent dynamics are pretty straightforward. Many features you can just calculate on pen and paper or Mathematica. And in general, maybe, although this is a perfectly plausible scenario, the dynamics are perhaps not the most interesting. In contrast, I'm going to focus on the post-inflationary scenario in which the Pecha-Kun symmetry was unbroken during inflation or was broken during inflation and subsequently restored, for example, by finite temperature effects. And in this case, over what is now the observable universe, the axion field was initially random, probably sampling values from 0 to 2 pi evenly. This leads to interesting dynamics because we get topological strings. These correspond to regions of space where, as we do a loop in physical space, we do a loop of the vacuum manifold. So that going around this loop, the axion field value goes from 0 to 2 pi. Just counting dimensions, or if you like, looking at homotopy groups, you can see that as a result, we get topologically stable objects that are string-like. These strings have a thickness that is set by the mass of the radial mode, and they have a core size. Well, the core size is set by the mass of the radial mode, and on this core, the radial mode is effectively forced onto the top of its potential. And then away from the core, the radial mode sits in its vacuum, the axion field winds. I'm particularly going to focus on global strings. So these are cosmic strings coming from the breaking of a global symmetry as associated to, for example, an axion. And an important feature of these is that the string tension is logarithmically divergent. So the string tension, that is the energy per unit length, has an expression that looks like this. We get a contribution pi Fa squared from the energy of the core, but then we also get a log divergent contribution coming from the gradient energy of the axion winding away from the core. This divergence is cut off in the UV by the size of the core and in the IR by the distance to the next nearest string of, say, opposite winding or opposite orientation. In the early universe, we'll see the typical distance between strings is set by the Hubble distance. So this tension has an expression of this form, and as the universe evolves, Hubble parameter decreases, the string tension grows logarithmically. Okay, so then we can look at the full evolution of the network. First, at some early time, we have the string network forms when the temperature, say, drops below the axion decay constant. We then get a network of strings. These evolve in some complicated way. Even though one individual isolated string is topologically stable, if I have a closed loop, this can collapse. If I have multiple strings, these can intersect with each other, they can interact and so on, leading to complicated dynamics. This persists all the way down until when the Hubble parameter is roughly equal to the mass of the axion, at which point the potential in the axion direction becomes relevant, and this leads to the formation of domain walls that eventually destroy the network, such that all we get left over with today are relic axions, which might make up dark matter, and gravitational waves, which we might hope to detect. And my aim in the first part of this talk is to show how we could predict the abundance of these axions, in which case we could, at least for the QCD axion, predict its mass, because the only unknown or the only unfixed parameter we have in our theory is the axion decay constant. And we could also predict the stochastic gravitational wave background that we might hope to search for. In some ways, this should be a reasonably straightforward challenge. The occupation number of the axion field throughout this time is huge, so the system is extremely close to a classical system, just following some simple equations of motion. However, we have a challenge due to two effects. So first of all, the dynamics, as I said, are nonlinear, and there's little hope that we could analytically solve for the evolution of the full system. You can maybe do something for a small perturbation away from a circular loop, but for any complex true string configuration that's realistic of what we expect to have in the early universe, you just can't solve the equations of motion. On the other hand, we also, as we'll see, have a large scale separation in our problem, which makes numerical approaches of simulations challenging. So to say a bit more about the second, what we would like to do is take our complex scalar field, say, discretize it, put it on some lattice, and then just solve the equations of motion on some supercomputer. However, in order to correctly capture the dynamics of the network, we first of all have to have a few lattice points per string core, represented by this circle. This is just so that we correctly, for example, resolve the dynamics when two strings approach each other, whether they pass through each other, whether they recombine, and so on. But on the other hand, we also need to have at least a few Hubble patches represented by this blue box in our simulation, because this is the typical length scale over which axion strings can interact. It's also the scale of which the axion string curvature is typically for the long strings, and so on. Now, memory constraints limit us to systems with, say, maximum 5,000 cube grid points, maybe if you really push your computing power 10,000 cubed or something like that. But this means that in simulations, we can only access values of this logarithm, which sets the string tension, that are roughly less than, say, 8 or 9. Whereas the majority of the axion dark matter, and actually also the majority of the gravitational waves, would be produced much later in the history of the universe, when the typical value of the log is about equal to 7. This is not just a small problem. We've already seen that the tension of the strings depends on this logarithm. We'll see later that within an effective theory, the coupling of the strings to the axion depends on this logarithm, or the inverse of this logarithm, which means that the interaction between strings over large distances also depends on the logarithm. So if we just do the naive thing of take our system, put it on a supercomputer immediately, then we're studying a system which is very far from the physical regime. Instead, what we have to do, or the only thing we really can do, I think, is do simulations at small values of the log, and then to try to do this, in principle, huge extrapolation to the regime that we care about. One thing that gives us hope that this extrapolation may be possible is the existence of a scaling regime. So at this, I got an approximate scaling regime. So this I can motivate pretty straightforwardly. You could imagine that if I have my string network, then maybe it looks something like this. I have one long string, I have some loops, I have maybe a big loop over here, and this box is telling me the size of the Hubble distance at some initial time. As time progresses, the strings will interact, maybe this loop collapses, maybe this loop pinches off or something, maybe these two strings recombine, such that at later times I end up with a configuration that looks a bit different. And you can imagine that provided I arrange my initial field configuration, my initial string configuration appropriately, I might be able to set up a situation where at later times the system looks just like it did at previous times, but just rescaled up. So in this case, there's still one long string, there's still one loop, and statistically, maybe having done so, the network is in some sense scale invariant. Actually, even better, not only does this scaling solution exist, but it's an attractor of the evolution. Again, I can motivate this in a hand-wavy way. So if you imagine that I have an overdense string configuration with many loops, a Hubble patch, many long strings, there's going to be very efficient interactions between the strings in such a way that at later times, many of the strings will have annihilated away, and I'll be drawn towards this, if you like, critical point where the rate of string interactions balances the rate at which strings re-enter each other's horizon. Conversely, if I have a very underdense string network, very little is going to happen. The strings are mostly going to be frozen, and strings will accumulate within the horizon by just re-entry. Okay, so given this scaling solution, it's useful to use this variable psi, which measures the length of string in Hubble lengths per Hubble volume, such that on the scaling solution, we expect that this dimensionless parameter may be approximately constant and maybe has a value that is not too far from 1. And just to remind you, the formula for the string tension is this. Okay, so quite a few years ago now, we did simulations. We run our simulations forward in cosmic time, which corresponds to the logarithm increasing. So in all of these plots, cosmic time or simulation time is increasing to the right. And here I'm plotting this string density, dimensionless string density. We start from different initial conditions represented by these dots, and we see what happens to the string length subsequently. And you can see pretty clearly there is indeed an attractor solution that the system is drawn to. So this gives us hope that because of this attractor solution that is approximately scale invariant, we should be able to, or we can hope to, extrapolate to the physical regime. This is also the reason I didn't have to specify exactly the details of the initial field configuration. Regardless, of course, there are many different ways that a field can be random depending on the details of the breaking. But independent of that, provided it is sufficiently random that strings form, then I will get drawn towards this attractor solution. Okay, so then what I need is the energy emitted into axions and gravitational waves in order to get the number of axions and gravitational waves that are produced, and I also need the momentum distribution. So let me first look at the energy emitted. Now, just the fact that this scaling solution is maintained allows me to derive an expression, a straightforward expression for the energy density that the string network is emitted. So it's given by the string density, not surprisingly, given by the tension, again, not surprisingly, with factors of t just there to effectively make up the dimensions. Now, the first thing you notice when you look at simulation results in a bit more detail is that actually psi is not perfectly constant, but has a clear logarithmic evolution in time, at least in the regime that we can test in simulations. So I'll show results for both the fat system and the physical system. The fat system is just a slight modification of the original Lagrangian, which is not really physical, not really expected, but allows for cleaner simulation results. Whereas the physical system is really the Lagrangian that I showed before. But in both cases, you see that this is just the same plot as before, but now zoomed in and with a non-logarithmic vertical axis. We have an attractor which clearly grows logarithmically. So to me, this growth is not particularly surprising at all. If you think about the attractors being this self-organized criticality point where there's a balance between string interactions and string reentries, then we know that the properties of the string are changing with the logarithm. The tension increases, as I said, the coupling to axions is changing. So a slow drift in exactly where this critical point is as the properties of the system changes seems totally reasonable to me. Indeed, it's pretty generic in physical systems that if you have multiple scales, then there will be dependence of the properties of the system on ratios of these scales. This appears both in, of course, classical physics and also in quantum field theory. Now, we also don't know what happens at very large values of the log, but at least one reasonable expectation, again, as we'll see later, is that the axion strings might be gradually evolving towards being closer to Nambu-Goto strings, and in that case, simulations find that the typical string densities are pretty large, something like between 5 and 15. So it's pretty reasonable to expect that this growth will continue, at least for a substantial period of time in log. With that as an assumption, we fit psi in terms of some universal behavior with C1 and C0, and then some initial conditions dependence, C minus 1 and C minus 2. And if we extrapolate to the physical values, we indeed get psi is about 15 for the values of log that we care about. Okay, the next thing that we can check is that actually the energy being emitted in the simulations matches up to our expectation. So here, for all of the systems that I care about, the energy going into gravitational waves will be extremely subdominant to the energy being emitted into axions or radial modes. And in fact, in our simulations, aside from a few specific simulations where we do tests, we actually don't include gravitational back reaction. We effectively just linearize gravity and ignore the contribution of emission of gravitational waves back onto the strings, such that the strings can only emit energy into axions and radial modes. So with that assumption, or with this setting, we only have gamma A, the energy to axions, gamma R, the energy to radial modes, and we see comparing the energy emission to the theoretical prediction, which is actually given by this plus when you calculate a bit more carefully some subleading terms, we have perfect agreement. Slightly interestingly, even in the largest values of the log that we can reach, only something like 85% of the energy is going to the axions, and actually there's quite efficient emission also to the radial mode. This does, however, seem to be gradually decreasing, which would be consistent with some sort of slow decoupling, which you'd expect on physical grounds. As the string curvatures get small compared to the mass of the radial mode, maybe it becomes harder to emit radial modes and axions are favored. So with that, we're confident that we can predict the amount of energy going into axions from the string network. But in order to get the number of axions, which is what we want in order to predict the axion relic abundance, we also need to know the axion momentum distribution, in particular, the instantaneous emission spectrum. So let me call this dp instantaneous by dk as a function of axion momentum k. On physical grounds, we don't expect to have much emission at momenta below the Hubble scale, just because there's not much dynamics happening on those scales. And we also don't expect to have much emission at momenta larger than the axion mass, just because these are momenta inside the string core, if you like. And again, not much dynamics is happening on those scales. And in between, at least the leading order expectation will be some sort of power law. So the two kind of theoretical expectation or theoretical possibilities for such a power law would be 1 over k to the q, with q being strictly bigger than 1. In this case, when you go through the calculation of the axion number density, you see that this is a relatively soft spectrum, such that the majority of the energy of the string network is being emitted to modes with momentum of order the Hubble at a given time. As a result, we produce many axions, each of which has relatively little momentum. But in the end, the axion momentum isn't important for the relic abundance. What we care is the number density produced. The opposite possibility is maybe we have again 1 over k to the q, but now to the power 1 rather than power bigger than 1. This is conversely a hard spectrum where actually the axion energy, or the energy of the string network, is equally distributed in log intervals between h and fa in such a way that the average momentum of the axions produced is now larger by a factor of log. So here this is k to the minus 1, log is on the denominator, typical k is large. As a result, in this case, we get many fewer axions produced, each of which has a larger momentum in order to account for energy conservation. So we would like to distinguish between these two possibilities with simulations. And just to illustrate, this makes a big difference to the predicted number of axions and the predicted eventual relic abundance. So this is what we can get from simulations, tiny values of the log. And depending on whether q becomes large or stays equal to 1, or becomes equal to 1, then the eventual axion number density is very different at large values of the log. Whereas actually if q is less than 1, you end up with very few axions, all of which have very high momentum, or the vast majority of which have very large momentum. Okay, so we can extract our spectrum from simulations of different values of the log. This is the overall spectrum, but more interesting is the instantaneous spectrum. So this is effectively an instantaneous spectrum, just factoring out dimensionful stuff such that f is the function that integrates to 1, with x effectively representing the momentum, or where the momentum is between Hubble and the mass of the radial mode, and y representing just different times. So these are results from the fat string system plotted at different values of the log. And here I've multiplied by a factor of x, such that q is equal to 1 would be a horizontal line, Q less than 1 would be, which is a very UV dominated spectrum, would be tilting upwards, and Q greater than 1 would be tilting downwards. And we can clearly see that for small values of log, this spectrum is very UV dominated, but there's a clear trend where as we go to larger values of the log, the spectrum is becoming more IR dominated. And this might have some kind of natural interpretation again in terms of decoupling, that maybe the high momentum modes are decoupling from the evolution of the strings, which is mostly on large distance scales. So plotting the value of Q as a function of log that we get, we again see a clear logarithmic increase. Unfortunately, we haven't quite got sufficient reach to extrapolate this beyond 1. It would be ideal to have data points that are all the way up here so that we could see a definite growth beyond 1. But to us, we see no evidence of this spectral index saturating at 1. And it would seem to me to be the minimal thing just to extrapolate and say that at large values of log, this, as far as we can tell, becomes IR dominated. We can also repeat the same exercise for the physical string system. In this case, the spectrum is a bit more messy, but still, again, we see the same trend of an increasing value of Q as log increases. Okay, I won't go through the details, but let me just note that there are various complications at around the time when the axion mass turns on. Specifically, if the spectrum does become IR dominated and if the growth in the string number density continues, then in this case, actually we end up with some non-linearities around this time. This is because the QCD axion mass is strongly temperature dependent. As QCD becomes strongly coupled at around GeV, the axion mass increases fast, and as a result, the field configuration has some interesting nonlinear effects. These modify the axion number density, they reshuffle the axion momenta between different values, and I'd be very happy to discuss these in some of the interactive sessions if people are interested. Okay, but you go through those complications, you do some more simulations to understand the nonlinearities properly, and we arrive at this prediction for the axion mass, which for the QCD axion, which is really, we can immediately relate to a value of the axion decay constant that is less than, say, 10 to the 10 GeV, which in terms of the type of plot I showed earlier, puts us somewhere to the right of this prediction for n domain wall is equal to 1, and for n domain wall bigger than 1, we have a value that is somewhat larger. I should stress that these are lower bounds on the axion mass because we could also have additional contributions from the axion domain walls, which we don't attempt to simulate. Now let me move on to gravitational waves. So now I have to do basically the same thing. I have to get the energy that the network is, predict the energy that the network is emitting into gravitational waves, and I have to predict the momentum of these gravitational waves. To get the first one, I need to make use of a bit more heavy machinery or a bit more theoretical machinery. This is not going to be used directly, but is going to motivate the extrapolations and give some physical understanding to the extrapolations of simulation results that we're going to do subsequently. So what I use is the effective theory of a axion string coupled to axions. To set this up, I trade the axion for a two-form capital A with the identification that the derivative, exterior derivative of capital A is related to the original field A in this way. And I describe my string in the usual way with worldsheet coordinates tau and sigma, and with its position in space-time represented by capital X. So then the action of my theory looks like this. I have the usual Nambu-Goto action, which is what you'd expect for a thin string. I have my axion kinetic term, which can be written in this form. And then I have the coupling between the axion string and the axions themselves of this form, which is just a Cobromont action. You can actually derive this effective theory as the long wavelength or low energy limit of the simple complex scalar fields Lagrangian that I wrote down earlier. But you could also just expect it on very general grounds that this is the only thing. These are basically the only leading order things that you can write down. Maybe the important thing to note here is that the coupling between strings and axions is set by the axion decay constant. This is required based on periodicity of the axion field around the axion string, so we have no freedom there. Okay, starting from this action, we can just work out the equations of motion of the strings and the axions. They're given by these expressions, nothing too exciting there. But maybe let me stress that this effective theory necessarily breaks down on distance scales comparable to the string thickness, as arise, for example, when two strings cross, or if there's some cuspy regions on the strings with curvature that is large compared to the thickness. So our effective theory could capture the emission of axions and gravitational waves in this kind of regime, but it will necessarily miss or not be able to predict processes like this. Maybe the other thing I can point out here is that we can now understand what I claimed earlier about the coupling between strings and axions depending on the value of the logarithm. So you'll see here that on the left-hand side, I have the string tension, and this string tension within the effective theory is logarithmically varying. I have to pick cutoffs in the IR and the UV, and the cutoffs I choose should be of order log MR over H in order to accurately capture the dynamics of the system. So then just dividing both sides by mu, I see that the coupling decreases as between strings and axions decreases as the logarithm decreases, which is what I claimed earlier. Okay, so now putting aside this concern about the effective theory potentially breaking down for the moment, let me just press on. With this straightforward calculation, you can show that the axion field is sourced by the motion of a particular string in this kind of way, whereas the gravitational waves are sourced in this way. Not surprisingly, this involves the axion decay constant, and this involves a Newton constant and the stress energy tensor. And the stress energy tensor involves the string tension. Then doing the calculation, you can show that for a particular string trajectory, the rate of energy emission into axions is given by an expression of this form, where crucially this RA of the string trajectory x is a dimensionless functional that depends only on the shape of the string motion, not on the overall scale, anything dimensionful, with all the dimensionful stuff coming from the axion decay constant Fa. And then similarly, the energy radiated into gravitational waves is given by an expression of this form, where this is another different dimensionless functional with the dimensionful stuff coming from mu squared with just a factor of g to make up the dimensions. Just as an example, I've shown here the functional for gravitational wave emission is not particularly insightful, it's just something you can work out. Then the crucial assumption, or the crucial step that we will check, is that if on average the shape of the string trajectory stays the same in the scaling solution, you might hope that on average, averaged over the full string network, the value of this dimensionless functional divided by this dimensionless functional might be constant in time. If this is the case, then we can say that the relative instantaneous emission to gravitational waves compared to axions is given by some constant just multiplied by this dimensionful stuff. And in fact, this also justifies what I said earlier about assuming that the majority of the energy goes into axions. Typically, we're going to be looking at values of mu string tension that are way below the Planck scale, such that this ratio of dimensionful stuff is much less than 1. And as long as this constant r is not too far from order 1, much less energy will be going to gravitational waves than axions. So if this ratio is indeed a constant, then we can now make use of energy conservation to put in that gamma axion is given by the string number density times the tension divided by t cubed, such that we get that the energy to gravitational waves is given by r times t mu squared over Fa squared times gamma being the total energy the network is emitting. Interestingly, this has a log to the 4 dependence. So first of all, we get 2 powers of log coming from the mu squared because the string tension is just increasing, which means that relatively more energy is going to gravitational waves compared to axions, of course, with gravitational wave energy still very subdominant at all times. We also have another factor of mu inside the total energy that the network is emitting. And finally, we have a factor of mu coming from the string number density increasing with time. Okay, now given that the effective theory I said is not guaranteed to work for all interactions in the network, we should check whether this does actually hold. So here I'm going to plot the instantaneous emission to gravitational waves divided by the total emission, but factorizing out all of the log to the 4 dependence. So I take gamma g over gamma, and I divide out g mu, the theoretical prediction squared, such that if this, effectively what I'm plotting here, is the value of this parameter r at different values of the log at different simulation times. So you can see that both for the PhET and the physical system, r is very close to constant within statistical uncertainties. And certainly we don't have here something that looks like a dependence that is linear in log or linear in 1 over, or goes as 1 over log or 1 over log to some power, which tells us that this log to the 4 dependence that we predicted is indeed genuine, and it seems that the effective theory is actually working. As a cross-check, we can also plot the total energy in gravitational waves as a function of time. This gets another factor of logs, so we get log to the 5 dependence total in the total gravitational wave energy density. Okay, then the final thing we need is the gravitational wave spectrum. This was the thing that was more complicated for the axion emission. Actually, here it turns out to be reasonably straightforward. We find that already in simulations, the majority of the energy is going to relatively IR gravitational waves with energy of order, momentum of order, the Hubble parameter, and a power law Q that is equal to 2, so definitely bigger than the critical value 1. And actually, as soon as this power law is sensibly bigger than 1, it doesn't matter exactly its value. It doesn't matter whether it's 2 or 2.5 or whatever. The net result for the spectrum is always the same, basically the same to within all the other uncertainties. Okay, then the final thing we need to do is reconstruct the spectrum today. To do this, we integrate over the emission at all different times. And what we get out is some expression that looks like this. We have a dependence on the parameter r that we extract from simulations, dependence on FA, and we have some residual log dependence just because if we have emission at earlier times, then this is happening dominantly when the value of the log is a bit smaller. Emission at later times, the value of the log is a bit bigger, so we get a bit more enhancement from this log to the 4. And going back to the spectrum, the sensitivity that I showed earlier, these are the results we get out. So for different values of FA, we get different dependencies. We can immediately see that for the values of the FA relevant for the QCD axion of about 10 to the 10 GeV, we would not get any observable gravitational wave signals, at least from the strings. So instead here I'm thinking more likely this would be relevant for an axion-like particle, in which case the value of FA can be much larger. And I've also assumed a pretty small value of the axion mass so that the network is destroyed long after the time when the gravitational waves relevant for, say, pulsar timing arrays are emitted. Okay, let me just briefly mention that the relic axions that get produced by strings lead to interesting substructure. So the idea here is that when the strings are destroyed, their typical scale is of order the Hubble parameter, and the number of strings per Hubble patch is in some sense a random variable. There might be more strings than some Hubble patches, less than fewer in others, and so on. This results in regions of space where there are more axions or less axions, and these have been historically known as axion mini-clusters. In particular, if we have order 1 fluctuations on co-moving scales of order, the Hubble parameter, when the network is destroyed, then we expect that the peak of the spatial distribution of axions, at least the co-moving peak initially, is set by h star. The standard story is that these perturbations would be frozen until matter radiation equality, when they would collapse into gravitationally bound mini-clusters. They'd then go through hierarchical structure formation before being bound into adiabatic halos. What I'm going to claim is instead that wave effects are relevant at around matter radiation equality. Since I'm running out of time, let me just say that this is characterized by a length scale called the quantum gene scale, associatedly a momenta k genes. And it turns out that for an axion-like particle, the peak of the fluctuation, the distribution of fluctuations, coincides exactly with the quantum gene scale at around matter radiation equality, which means that the things we get out are actually axion stars rather than axion mini-clusters. So our claim would be that for axion-like particles, we have perturbations that are frozen, and then they collapse into solitonic axion stars rather than mini-clusters, which are more like small versions of the standard halos that we see around us. So specifically, axion stars are solitonic objects that are with the gravitational potential balanced by quantum pressure. Okay. So this is a result from simulations we do around matter radiation equality, and the different colors represent different densities in space, with these red dots that you can see being axion stars. In fact, we claim that the same thing also happens for the QCD axion, in this case due to self-interactions at around the time when the axion mass turns on, again due to the fast increase in the axion mass. And we would say that somewhere in the region of between 10 and 20% of the axions are bound, in the QCD axion case, are bound into these axion stars at around matter radiation equality. These things have a typical radius that is something like 10 to the 6 kilometers. They have densities of order electron volt to the 4, and masses of, say, 10 to the minus 18 or 10 to the minus 19 solar masses. Perhaps interestingly for these, because they are relatively light and because they have relatively low density, even though they're much denser than the background dark matter density, these axion stars could collide with the Earth on a pretty experimentally interesting timescale. So taking our parameters, you would say that the average time on which an experiment on Earth would see a collision would collide with an axion star is something like once every 5 years. And during this time, the experiment would see an enhanced density for something like 8 hours, during which time the axion abundance would be a factor of 10 to the 6 larger than the background that the experiment would see the rest of the time. So direct detection could be plausible, and maybe there are opportunities, and perhaps this would favor things like broadband approaches, which could simultaneously be experiments that could be sensitive to all axion masses at once. There's also potentially other opportunities. You could maybe make use of the fact that the axion field within these stars is extremely coherent. Okay, finally, in the last 2 minutes, let me briefly mention some recent work on metastable local strings. So local strings are like axion strings, but now with the symmetry gauged. In this case, the majority of the energy density is localized in the string core. There's no energy from winding far away from the string because I have a gauge field that can cancel off the gradient contribution, if you like. And an interesting scenario is when I have a breaking pattern like G goes to H goes to K, such that the overall breaking does not allow for strings. The first homotopy group of G mod K is trivial, but this intermediate stage is not. So a simple example would be SU2 breaking by a scalar adjoint to U1 breaking to nothing. This second stage leads to strings, but overall there's no topologically stable string configurations. And instead what I have is strings that can end on monopoles. Now, if I have a cosmological setup where the first breaking happens at, say, this energy scale, the second breaking happens at this energy scale, and I reheat to an intermediate temperature, I can form a string network due to this phase transition, resulting in strings that are not perfectly stable but are pretty long-lived. The standard picture here is that these strings would subsequently break by vacuum decay, by quantum tunneling effectively, such that a monopole-anti-monopole pair is spontaneously produced on strings, leading to the string network being destroyed at this kind of time, and a gravitational wave signal that would cut off at some characteristic frequency, depending on the ratio of, say, the monopole mass to the string tension, square root of the string tension. We've claimed in a recent paper that actually this is not the dominant, may well not be the dominant process that breaks the string network, and actually breaking at early times dominates, leading to string segments that are extremely super horizon initially, with this being the horizon size, but which are still nonetheless finite size, such that the string network is destroyed when these segments re-enter the horizon. Effectively, this boils down to the fact that at finite temperature, you have a breaking dependence on the monopole mass compared to the temperature that goes like this, whereas the vacuum breaking rate depends on mass of the monopole squared divided by the string tension. So potentially this exponential can be way, way larger than this exponential, leading to this one dominating. Okay, I won't say too much more, but I'm very happy to discuss this if anyone is interested. Okay, so let me just summarize that I've talked about the post-inflationary axion relic abundance and emphasized that careful extrapolation is needed. I've pointed out some enhancements in the gravitational wave emission from global strings, which are important to take account of if you are going to give predictions to observers. There's also interesting effects on the spatial distribution of dark matter axions from strings, specifically axion stars. And I very briefly mentioned that the cosmological history of metastable strings may be quite different to what people have assumed in the past. Okay, thank you.